So let's do it. So remember what it means to graph an equation. What we want to find is find all x, y points satisfying, well, this equation. Y equals x squared over 2. And one way we can do that is let's just fix some x values. We can determine the y value that solves the equation. Once we know the x value, we'll just plug in that value for x. We'll see what we get. When we plug in x equals -3, well, we go through the walk. Y should be -3, replace x with -3, divided by 2. -3 squared becomes 9. 9 halves is 4.5. So over x equals -3, we should see y equal to 1, 2, 3, 4.5. So this point, -3, 4.5, will be on the graph of this equation. And as we progress through the class, we'll develop a few tools a little bit more sophisticated than what we'll do right now. We can get a pretty good idea for this graph just by doing like 5 more computations. When you try to plug in x equals -2, what do you get for y? 2. 2? Great. Does anyone want me to go through the walk of doing the computation? Okay. Plug in -2, you get 2. So the point -2, 2 will be on the graph. When you plug in -1, a half. When you plug in 0, you get 0. And maybe you believe that if you've done this computation for all negative values of x, you've also done the computation for all positive values of x. Squaring forgets about the negative sign. That's the first thing it does. So erasing the negative sign can't change anything. And we get already a pretty decent feel for what this graph is going to look like, just by connecting with straight line segments. Fair enough? And, well, you can answer questions about this function now that you see some patterns emerging. It looks like as the x values start at 0 and keep going left to right, the y values get bigger. And in fact, they get bigger at a rate that increases. That graph keeps on getting steeper as you go left, as you go right. For negative x values, you see exactly the opposite. The slope of that graph appears to be negative. The farther away from 0 you get, the more negative that slope is. And what do you think? Would we have been able to get a better picture of the graph if we had plugged in more values? Yeah, we could have plugged in multiples of a half. We could have plugged in multiples of the third. And when you have a computerized graph a thing, that's exactly what it does. It just plugs in like a billion points in the time it takes me to evaluate one. I'm slow for a human. Computers are pretty quick. There are just a few more things I want to mention about graphs in these notes. So there are two data about graphs that I'll want to mention. The first is, what's the x-intercept? This is just a word. The x-intercept of a graph is all points where that graph hits the x-axis. Fair enough, and that seems like a reasonable name. So in the example that we just did, what does it look like the x-intercept of that graph is? 0, 0. And so you draw the x-axis. You say, oh yeah, there's the only point where it hits the x-axis. The y-intercept is the same, but replace x with y. All points where that graph hits the y-axis. Same question for that graph. What is the y-intercept? Also 0, 0. X-intercept equals y-intercept equals the origin. Fair enough? And whenever you have a picture of a graph given, you can read off the intercepts. So for this last graph on page 5, computer generated, where does it appear that the x-intercepts are? Be approximate. Yeah, maybe I'll make one comment. That definitely conveys all the information. You've specified the x value. What's the y value of an x-intercept? Always 0, because it's on the axis. But an x-intercept should be a point. So maybe I would prefer to see negative 2.5, comma 0, and 6.5, comma 0. What I'm feeling in my most pedantic of moods. Similarly, what are the y-intercepts? Yeah.
Negative 2.5 and 2.5. I mean, negative 2 and positive 2.
Okay, that seems more reasonable. I mean, again, this, you can't be 100% confident that it's exactly at 2, but it sure seems to be. And again, I'll demand that I put them in the form of a point. Everyone feel pretty okay? That works out? There's one last thing to say. So this is very much a graphical technique. You look at a picture and you find those points. But a lot of times we'll want to get a handle for where the intercepts are by doing purely algebraic stuff. And let's think about how. Algebraically, you can find the x-intercepts of the graph of an equation somehow. So let's see, an x-intercept is where a point crosses the x-axis. What's special about a point on the x-axis? Yeah?
Y equals 0.
The y value is 0. So if you want to find an x-intercept, it looks like you're looking for all points where y equals 0. So if you have an equation, what you need to do is you need to set y equal to 0. And I guess if you can solve for x, that would do the job. And in talking through it, it seems clear, but maybe I'll point out that if you're thinking too quickly and you think you want x-intercepts, if you're being too intuitive, you might just say, well, let's just set x equal to 0 because I want x-intercepts. That will be exactly the opposite of what you want to do. So that's a caution to be on. Let's say you want to find the opposite, y-intercepts. What's special about a point on the y-axis? X equals 0. So if you want to find the y-intercept, do the exact same, but set x equal to 0, solve for y. And let's just do one of these two exercises. And then we'll move on to the content that I actually want today to be about. So let's find the y-intercepts of the graph of x squared plus y squared is equal to 1. So to find y-intercepts, what do I need to do? Set x equal to 0. Oh, I guess it said that. And what will that become? You'll see 0 squared plus y squared equals 1. Y squared equals 1. What's the solution to that? Just loud order.
Square root of
1. 1 is the square root of 1. But you're missing a solution.
Plus or minus.
Plus or minus. Whenever you undo a square with a square root, you lose information. Right. Negative 1 also has the property that its square is 1. So that might seem like it's the whole answer, but I want the actual coordinates of the point. So what are the points that are the are the y-intercepts? Yeah.
0, negative 1, 0, 1.
Yeah, just those points with zeros in the x-coordinates. Any questions about this stuff before we move on to something else? Okay. So I want to explore this idea of functions in more detail now. how many people are going and investing in like a binder for the sake of this class? Yeah, that's kind of my intention, right? I'm going to give you notes every day. They'll even, for the most part, be hole punched, except when I forget to hit the hole punch button, which will happen sometimes. And by the end of it, you'll have approximately a textbook's worth of notes. So let's talk about functions. So a function is any quantity which you can compute given another quantity. Yeah.
Can I have one copy?
Oh, yeah.
Thank you.
Did I show it on anyone else? Oh, there's some coming to you.
Oh, awesome. Thank you.
I'll take one, probably.
Perfect.
Thank you.
Anything else? Perfect. So a function is any quantity which can be determined given another quantity, and you encounter those all the time. Like, let's do this quick modeling problem. So if you stand on the ground, take a bowling ball, and throw it vertically with an initial velocity of 20 meters per second, then until the moment that the ball lands, you can model the height of the ball with the following function. -5t squared, so some term that has to do with approximately how strong the force of gravity is near the surface of the Earth, and some term that has to do with its initial velocity. People feel good enough? How many people are physicists in this room? Oh, okay. That 5 should really be closer to like 4.98, but 5 is close enough to 4.98 for my hypothesis. So let's walk this through. So given this model, at t equals 0 seconds, what should the height of the ball be? Yeah, right? It should be 0, and there are two ways to see it. On the one hand, at time equals 0 seconds, you haven't actually let go of the ball. You're still carrying it. It's still at the ground. On the other hand, the way you compute any of these is I'm literally going to plug in 0. This will be -5 times the quantity 0 squared plus 20 times 0. And of course, that all shakes down to 0. People feel pretty good? Can we determine the height at time equals 1 second after you throw the ball? Yeah.
So
15 meters, I guess. Like, the units are important here. Fair enough. You just plug in 1, see what happens. You can plug in t equals 2. You'll get h of 2 equal to -5 times 2 squared plus 20 times 2. Well, let's see, 2 squared is 4, so that's 20 meters. In general, if I give you a choice for time, can you use this formula to determine what the height is at that time? That's a function. And I think I want to just do 2 more things in the margin here. I think I want to say also that the height at 3 is also 15 meters. You could compute that to find that fact. And the height at time equals 4 seconds is back down to 0. So if we try to plot this, at time equals 0, it's at height 0. At time equals 1, it's at 15 meters. At time equals 2, it's at 20 meters. 3 back down to 15, 4 seconds down to 0. The flight of this ball is that, give or take. So all a function is it's some rule which takes things from some set, A, generally it'll be a set of numbers, to some other set, B, generally also a set of numbers. The domain of a function is all valid inputs for that function. Is the screen actually readable? Is there any like focus issue? It's readable in the back? Okay, good. So in this case, when you're given a formula that models some behavior, you generally want to think of the domain of that formula as being all inputs for which that formula actually has the correct behavior. For instance, would you want to plug time equals -1 into that formula? On the one hand, like, why not? Well, like a second before you've thrown the ball, you're still just holding the ball, right? So presumably the height should be 0. Let's see what happens when you try to plug in h of -1. So that'll be -5 times -1 squared plus 20 times -1. Times -1. So this formula predicts that a second before you've thrown the ball, it is 25 meters below the surface of the earth, which is nonsensical. So in this case, for this particular function, you should only consider inputs for which the height of the bowling ball is given by the formula. So its domain will be all t values with h of t bigger than or equal to 0. But by looking at this little graph that we've drawn, it looks like height is negative well, this formula will give a negative height as soon as time is negative. And it gets back to the ground after 4 seconds. Beyond 4 seconds, what do you think the height will be? Yeah, this formula will predict negative, but what will the height actually be? If you take a ball, you throw it in the air, and then let it land, and then keep watching it, what's the ball going to do? It's just going to sit there. The height will continue to be 0. So this formula doesn't have the right behavior. Looking at this graph, the domain is 0 to 4. And let's see what happens when we try to plug in t equals 10. Somehow you already know what's going to happen. We try to plug in 10. We'll get -5 times 10 squared plus 20 times 10. Let's see, that'll be 10 squared is 100. So that'll be -500 plus 200. That's -300 meters. So this formula predicts that if we throw the ball up in the air and wait 10 seconds, then the ball will have poured 300 meters into the earth, which, again, is nonsensical. So we'll just correct this by saying t equals 10 is not in the domain, which is why we demanded that the domain should be 0 to 4. Any questions so far? Cool. So, the next thing to mention is the set of all realized outputs of a function. We'll call that the range. So in this case, the range is all of the values that height actually takes from time equals 0 to 4 seconds. Looking at this graph, it certainly looks like the ball is at its highest when time equals 2 seconds. The ball's at its lowest at 0 seconds at 4 seconds when height is 0. So the least the height, minimum height, the maximum height is achieved at t equals 2 seconds. What was h of 2 again? 20. The maximum height is 20 meters. The minimum height is 0 meters. So what do you think, what are all of the heights that this ball actually attains? Is the ball ever exactly 10 meters off the ground? Well, it should be, right? If I throw a ball in the air, it starts at 0 meters, it makes it up to 10 meters. There should be some moment when it makes up to 20 meters. There should be some moment when it's 10 meters off the ground. The ball can't teleport past the 10 meter mark to get to the 20 meter mark. So it sure looks like the range is all values between 0 and 20 in meters. Yeah. What's another name for the set of all values that are between 0 and 20? What's an interval, right? That's the interval from 0 to 20, including or excluding 0 and 20. Is the height ever exactly 20 meters? No. At time equals 2. Is the height ever exactly 0 meters? So should those be included or excluded? Okay. So the range of this function is exactly 0 to 20. And again, just for emphasis, this is all in meters. Any questions so far? So, as is my habit, I'm going to forget a little bit about explicit applications for a bit, and I'm going to go to the abstract. Just let's take functions given by formulas and walk directly with them. So, here's a function, f of x equal to x over x plus 1, Gesundheit. For that function f of x, how can you compute f of 2? Well, I guess the other question is just what is f of 2? Guess it's 2 thoughts, I think. And how do you do that? Well, you literally just plug in x equals 2. You can take a function and plug in something more complicated than a number. You can plug in a formula. If you want to compute f evaluated at x minus 2, I'll just take all the x's and replace them with x minus 2's. So I'll get x minus 2 divided by x minus 2 plus 1, also known as x minus 2 divided by x minus 1. People feel okay about that? And the buzzword for what I just did is function composition. You can compose functions together like that. If you have another function, say x squared plus 1, you can plug that function into f by doing exactly that. If you want to compute f of g of x, I'll replace all the x's with g of x's, so that'll be g of x divided by g of x plus 1. What is that? That's just x squared plus 1 for g of x divided by x squared plus 1 plus 1. So x squared plus 1 over x squared plus 2. Fair enough? Once you have functions, you can plug things into them. You can evaluate functions. You can even evaluate functions at other functions. You can add functions together. If I add f of x to g of x, I'll get x over x plus 1 plus x squared plus 1. So let's just read off some things. Take a look at that function f of x. What is its domain? And let's read it off this way. So the domain is all things that you can actually plug into the function. Well, in order to think about that, let's think about what's going on here. So I see just an x in the numerator, an x plus 1 in the denominator. So x can be a number. Is there any number that you can't add 1 to? No, that always makes sense. So you can always add 1. But you have an observation, I think.
If you add -1, it equals 0 on the bottom.
Yeah, there's a problem if you plug in -1. You'll get a 0 in the denominator. So let's see, when you plug in x equals -1, you get a division by 0 error. So that means -1 isn't in the domain. Which maybe I'll summarize by just saying x equals -1 is bad. Are there any other numbers that are bad for this formula? No, you can always add 1 to a number. You can divide, you can have anything you want in the numerator of a fraction, but you can't have a 0 in the denominator, and that's the only bad thing that can happen. So the domain, I'll write it a few ways, is all numbers but -1. Or we can say that in interval notation also, because that'll be all numbers except for -1. So I just need to exclude -1. So you could write that as all numbers less than -1, and then all numbers bigger than -1. So you could write that as -∞ to -1 together with -1 to infinity. So both of those are correct answers. Any questions so far? So if you want to find a domain given a formula, just think about what you can't plug into that formula. Find the bad numbers. What about g of x? Well, that function g of x given above, what is its domain? Well, let's see. G of x requires you to take x, square it, and then add 1. Is there any number that you cannot square? No, you can take any number and multiply it by 1. You'll always get a number. Is there any number you can't add 1 to? So nothing bad happens. There are no bad numbers. The domain of G is all real numbers. Or if you like interval notation, -∞ to infinity. And maybe I'll even permit one bit of just formal symbology. To denote all real numbers, I'll use a blackboard boulder. So that's a good answer. That's a good answer. All right, well now let's think about f plus g. Let's think about it this way. So what are the numbers that you can't plug into f? Well, it's like 2 items above, right? Just -1 is bad. What are the numbers that you can't plug into g? You're cool plugging anything into g. It's always happy. So as long as x isn't -1, f of x will be a number, g of x will be a number. Are there any two numbers that you can't add together? No, addition is always defined. So the only bad number comes from f. So the domain is interval notation, -∞ to -1, together with -1 to infinity. People feel pretty good? So notice, I didn't actually have to think about exactly what f plus g is. I knew the domain of f, I knew the domain of g, I automatically knew the domain of the sum. It's everything that was simultaneously in both. That's always true. Given any two functions, you can always combine them to get a sum, f plus g, f minus g, f times g, or f divide by g. If you want to compute the domain of the sum, difference, or product, well, are there any two numbers that you can't add? That's always fine, right? Are there any two numbers you can't subtract from each other? No, that's always fine. Are there any two numbers you can't multiply? No, but they both better actually be numbers. So if you want to make sense of f plus g, f minus g, or f times g, both f and g better make sense. So the domain of any of these is just all inputs, which are simultaneously in the domain of f and the domain of g. And I think I'll skip out on the find a formula bits. So for these two functions, new functions, x plus 1 and x minus 1, let's figure out the domain of f plus g and f divided by g. Let's see, looking at f of x, what's the domain of f of x? All real numbers? So let's see, the domain of f is equal to all real numbers. The domain of g is equal to all real numbers. So for f plus g, are there any bad numbers? No. So what's the domain of f plus g? Yeah. Cool. Now let's think about division. Let's do it in the abstract form. So to make sense of f divided by g, f had better be defined. If f doesn't make sense, then dividing won't suddenly make it make sense. G had better be defined. I can't divide by something that I don't know what it is. So the domain of f plus g will only contain numbers that are both in the domain of f and in the domain of g and something else. What number can I not divide by? 0. So if g of x is 0, that number is not in the domain. So let's use that. So same question. Let's find the domain of f divided by g for these same two functions. So let's find them one at a time. What's the domain of f? Well, it's like also the line right above, right? All real numbers. What's the domain of g? All real numbers. So we just need to figure out when is g of x equal to 0. When is the denominator 0? So g of x equal to 0 is bad. So x squared minus 1 equal to 0 is bad. When is x squared minus 1 equal to 0? Yeah, just say it louder though. When x is 1 or negative 1. So x equal to plus or minus 1 are both bad. So the domain is all numbers but plus or minus 1. You can write this in interval notation as negative infinity to negative 1, together with negative 1 to 1, together with 1 to infinity. Does that seem reasonable enough? Both of those I would think of as being correct answers. Everything except for plus or minus 1. You could write that as an interval, as a collection of 3 intervals. Yeah, we're doing okay. I think I want to do just one more example of computing domains using this idea in order to emphasize that something subtle can happen sometimes. This will be item 4 on the next page, really. So here are two functions, x divided by x plus 1. Nope, x plus 1 divided by x, and x divided by x plus 1. What's the domain of that function f? Well, here's the way to think about it. What's the domain of the numerator in f? Everything, right? All real numbers. What's the domain of the denominator? Well, in some sense, if you don't know that it's a denominator, then it should be like all real numbers. You can always subtract 1. But when there's a 0 in the denominator, that's bad. When's the denominator of that function 0? X equals 1 is bad. And that's generally how you want to think about finding domains. Find the things that aren't in the domain. Then the domain is everything else. What's the domain of G? Well, what is the bad number for G? Negative 1?
Can you just pull the paper a little bit too?
Yeah, so that maybe I'll also do this in order to make it easier for me to stay on the paper. Is it still big enough to read? Okay. So the domain of G is all numbers but -1. So without doing any more thinking, what's the domain of f times G? Well, all numbers but 1 and -1, they're both bad. And then you could write that as an interval if you want, but I don't want to emphasize that. So here's why I'm focusing in on this example. That is the correct answer. It's all numbers but plus or minus 1. But let's also take f times g and see what it simplifies down to. So there's x plus 1 for f divided by x minus 1 times x divided by x plus 1. Does anything cancel in that? The x plus 1s? Nice. So what now do you think the domain is? Everything but 1. So here's the point. You check for domain before doing any algebra. Check domain first before doing any algebra. And the other thing, so what this means is x equals -1 isn't in the domain of the original function. But we could find a function that's basically the same that has a bigger domain. So here's a bit of notation that we won't use much. X equals 1 is a removable singularity. Singularity because you wind up dividing by 0, but removable because you didn't really need to divide by 0. That seem okay? And we won't use that word much, but it's a good word to be aware of. The main point is you check for domain before simplifying. So with those bits out of the way, I want to focus in on linear functions, which we introduced just a little bit last time. So a linear function is any function which you can write as f of x equal to mx plus b with m and b constant. Fair enough? That makes sense? Let's explore that a little bit. 9/5 x plus 42, is that a linear function? Folks, for yes? Yeah. What is m? What's b?
2.
There's another function, g of x equal to x times x plus 1. Is that a linear function? Folks, for yes? Folks, for no? Okay, good. I didn't manage to trick anyone. Because you may have been tempted to say that, well, it looks like m can be like x. But is that a constant? Well, how about this function, h of x equal to 3? Is that a linear function? Yes? No. So, you said yes in the back. What is m?
0.
0. All right, let's rewrite that a little bit. Notice it's not a function that is in this form. It's a function that can be put into that form. So is 3 the same thing as 0 times x plus 3? Yeah. Now does it look linear? And just to get a bit of motivation, those three functions, here are their graphs. The first one we said was linear, second one non-linear, third one linear. Let's just get some color coding in to emphasize. Of course, I can't trace a line to save my life. And the two functions that are linear and the one that isn't linear, how do they look different? Yeah, the middle one's a parabola. It's got some bendiness. The other two are lines. Linear functions are called linear because their graphs are lines. Their graphs are very simple. They're just straight lines. So with 10 minutes, yeah, that's enough time. So that in general, there's a philosophy that if you know two things about a line, you know that line. There are two parameters you need to specify on. You need M and you need B. So there are two facts that you need. And if you do some algebra, then in general, any two facts about a line will let you find those two things. And here's the one that's easiest to find. It comes from the idea of slope. So if you want to compute the slope of a line, there's a definition for what that should be. If you have a line, then its slope is just how much does it go up divided by how much you go across. So slope will sometimes be written as delta y, delta being a general symbol used for change in something, divided by the change in x. And, I mean, you know what change is. It's how much do the two coordinates differ. y2 minus y1 divided by x2 minus x1. Both of those that gives the slope. Well, how many people would rather write y1 minus y2 divided by x1 minus x2? That's the same though, right? As long as the order is consistent. Oh. So let's use that. Let's compute the slope of the line y equals 2x minus 4. On the one hand, how many people just staring at that already know what the slope will be? What should it be? 2. Somehow because there's a 2 in it. Let's just do a quick sanity check that it actually walks out. Let's find 2 points on that line. X equals 0, x equals 1 will do. When you plug in x equals 0, it looks like I get y equals 2 times 0 minus 4, so that's negative 4. So there's 1 point on the line, 0 comma negative 4. If I plug in x equals 1, I'll get another point on the line, namely y equals 2 times 1 minus 4, or negative 2. That tells me that 1 comma negative 2 should be on the graph. That's enough information to compute the slope. The slope is now change in y divided by change in x, negative 2 minus negative 4. So it looks like I'm doing this one first. Divided by 1 minus 0. Hopefully that actually simplifies to 2. I think it does. Groovy. So that actually matches up. The slope is 2. And let's just read it off from this. So the slope of y equals 3. What should the slope of that line be? 0, right? Y doesn't change at all, so delta will just always be 0. In general, the slope of any line, given by the formula y equals mx plus b, is just m. Aha! So now we have two different ways of deciding the slope. On the one hand, the slope is always the coefficient m. If we have 2 points on a line, we can compute the slope as delta y over delta x. I think I want to see that in practice just once. So let's play this. Let's here's the goal that I think I'll have. Suppose I tell you that 2 points are on a line, 1, 3, and 3, 2. So let's go ahead and graph that. 1, 1, 2, 3, and 1, 2, 3, 2. There are 2 points those 2 points specify a line. I'm not very good at connecting the dots, but you get the idea. We should be able to figure out exactly what line that is. Let's try to do that. So step 1, m is apparently just the slope, which we know how to find. So m, which is the slope, is exactly change in y over change in x. Well, now it's just computation. Let's pick a point to be the force point. That'll be 3 minus 2. All over change in x will be 1 minus 3. And my brain's feeling just a touch numb at this point, so I don't trust myself to do the arithmetic. What is that? -1/2. Okay, good. So, the equation for a line is something that is of the form y equals mx plus b. So that'll be my initial goal. But in general, you can think about points, equations for lines if you don't want a function in point-slope form. If you pick a point on the line, you get an equation for that line. In point-slope form. Do I know a point on this line? Yeah, in fact, I know 2. Apparently, it doesn't matter which one that I'll use. I don't know. Which point would you rather use? 1, 3, or 3, 2? People for 1, 3? People for 3, 2? Well, there's no reason to pick one over the other. So, but because some people raised their hands for 1, 3, I'm not going to do 1, 3. Because you all will do 1, 3, I'll use the point 3, 2. So the equation that I'm going to get is y minus 2 is equal to m, that's -1/2, times x minus 3. So that gives me an equation for the line. Is that in the form y equals mx plus b yet? So let's massage it just a little bit to get it into the right form. So I guess that means I should distribute the -1/2 and I should add 2 to the other side. So I'll get y equals, I'll go over to decimals, I think. Y equals 0.5x. Double negative will become a positive, plus 1.5. Add 2 to both sides. I'll get y equals -0.5x plus 2.5. And there's an equation for this line. Those of you who chose to use the other point and follow the same steps, did you get the same result? Yeah, great. So that's encouraging. It doesn't matter which point on the line you use. You'll always get the right answer. I have a minute and 20 seconds. Maybe I only have 20 seconds. In general, whenever you have 2 points on a line, you can find a linear function whose graph is that line by first finding the slope. Which is just m. Step 2, use point slope form to get an equation. And finally, the last step that I'll suggest doing, solve for y until you get something that's of the form y equals mx plus b. That seem pretty good? Cool. We'll start up with this and introduce a few new things tomorrow. Based on the progress we make tomorrow, the homework assigned tomorrow might get pushed around. Some of the problems might migrate to next week's assignment.
Is it okay if we have this one?
Here.
prefer a loose sleeve?
Oh, no, the paper's fine. Yeah.
Okay,
Yeah.
okay,
I'm going to make one complaint about it.
sure.
So, when I see this problem number 19, I see that there are apparently 2 points, but I'm not sure what the question is on this. So, some sort of problem stated that I
Okay, okay,
on the first assignment, I'll be reasonably forgiving.
okay. So you want to know what's going on?
Yeah, so, and that's for your benefit too.
Right.
The homework that you get back at the end should also solve as a self-contained stuff.
Okay.
And in like 3 weeks, you'll forget what problem 19 section,
Right.
Act 1 section.
Okay, okay.
So for one, you said top points, you say what quadrant, find all the points, and for B, it was 0, -3. I'm confused on what that was.
Yeah, so my convention is that doesn't follow.
Okay, that's-
falls between quadrants.
Yeah.
1 and 4.
So that would be changed to as a question mark?
Oh, right, something like not in a
Not
quadrant.
in the quadrant, okay, perfect, thank you.
Yeah. Have a good day. See you tomorrow.